All right, welcome to chapter 12, number 21. Chapter 12, number 21. So what we have here is we have a strut. We have a strut here, and it has a 225 kilogram block hanging from it from a cable, and then there's another cable over here that's attached to the ground, 30-degree angle, 45-degree angle here. And the first thing we have to do is find T, the tension in the cable. That's the first thing we have to do. So, to that, we're just going to jump right in. What we see here is that this is our strut. It's attached to the ground by a hinge and free to pivot. If it's free to pivot, this feels like it's a torque problem to me, and because it's not accelerating linearly or angularly, it's in equilibrium. Therefore, the sum of the torques, the net torque is zero. So let's make a net torque statement. First of all, I know the net torque is equal to zero. Okay. In order to make a net torque statement, what we're going to need is we're going to need a force diagram for our strut. So let's see if we can find out what the forces on our strut are. So let's draw it here. Okay. Because it's a rigid object that's free to rotate, we're going to draw it and then draw the forces on it where they actually act. So here's my strut. It itself has weight, and that acts at the center of mass. We're going to call that one little mg. Over here, we have this, it's the tension in this, which is also the weight of this, because that's balanced there, so we're going to call this one big mg. This string is pulling this direction. We're going to need to know that angle later, but this is our tension, T. And then the hinge down here has to be supplying some force. Now, these are two down forces. This is actually a down force also, which means that it has to be an up force, but it also has to be up and in. It has to balance out this force. And so we know it's somehow up and in. Now, I can't draw it to scale here because I don't want to overlap the rest of my forces. But this is the hinge force. We're going to call it H for hinge force. We know it has to be up and to the right. These on this diagram aren't clearly balanced, but we're going to go with it for now. So, if I go to do the torques, I got to choose a pivot point. I'm going to choose the hinge as my pivot point right here. And I'm going to have to figure out what these are. In order to do this, we have to figure out where they are acting. This one's acting all the way out at the end. This one here is acting at the end also. This one is in the middle. So let's just call our total length here, let's call it L. That way we have a referent. So, the hinge can't supply a torque because the R is 0. So let's do this first one here. Does this little mg supply a torque? It absolutely does. It would rotate if it could. It would rotate it would rotate clockwise, therefore it's negative. So negative, its distance is L over 2, little mg sine. Now what angle is this? So this is 45 here, which means this one would also be 45. So sine 45. I'm okay with that. What about this big mg? The big mg also would get it to go this way. It's also out at L, big mg, sine 45. Okay, and then what about the tension? Well, the tension is absolutely supplying a torque. It's also out at L, T. But what angle is this? This is interesting to me. This would be 45 if it were horizontal, but it's pulling down here. So, according to the diagram, this is a 30-degree angle, which makes this one 30. If the whole thing is 45 and that's 30, this has to be 15 degrees. So this is all equal to 0, which is cool. So if I get the, I can see the L's, I can divide through by L, those magically disappear. So I end up with, on this side, T sine 15 degrees is equal to 1/2 little mg sine 45 plus big mg sine 45. And what's nice about this problem now is the signs you can just put in your calculator. I know the big M, I know the little m, I know the g's. I can solve for this directly. And what I'm going to do here is I'm going to use 10 for this here. So this is sine 15 1/2. The little m is 45. I'm going to use 10. It's what, 225? 225. And when I solve this, I get the tension is equal to 6,759 newtons. Now, of course, in the book, they're using 9.8 instead of 10 for the gravitational field strength. They're also using 3 significant digits, so it's 6 point something something, and then they call it kilonewtons. So that's what they end up with. But what this does is it gives me a good sense of what the tension is. The next part says, what are the horizontal and vertical components of the hinge force? Well, in order to do that, what we're going to need to do is we're going to need to find out what the vertical and horizontal components are, which means we're going to need some net force statements. So let's do the net force in the x direction. First of all, we know it's equal to 0. The net force, what are the net forces in the x direction? Well, it's the hinge force in the x direction. We're going to call it hx. And then the only thing opposite of that is the tension in the x direction. Therefore, if you set these equal, the hinge in the x direction is equal to the tension in the x direction. But let's come up here and let's look at that. If I break this tension up into its component parts, it pulls to the left and down. So this is the T. I know the value there. This is my 30-degree angle. Isn't the Tx equal to T cosine 30? And if I just plug and chug that here, I have the tension, I have the cosine. Let me do it on my handy dandy calculator, 2 seconds. Okay, and I got 5,853 newtons for the horizontal. And then what about the vertical? What about the vertical? Well, if I look at the vertical over here, what do I know about the net force in the y direction? It's equal to 0. If I look at my force diagram here, the hinge is in the up direction. So I have hinge in the y minus little mg minus big mg, and also here minus the tension in the y direction. So when I go to solve for the hinge in the y direction, I have little mg plus big mg plus the tension in the y direction. But I know all of these. This is 45, 225, and this is the tension times the sine of 30 degrees. And when I plug and chug this, I end up with 6,079 newtons. And that's it. I got the tension, the horizontal, and the vertical. Oftentimes on the AP test, they want to find, well, what is the actual like force? But here they just ask for the horizontal and vertical, and that's enough.